In mathematics, the nth root of a number x is a number which, when raised to the power n, yields a x, where n is the degree of the root. A root of degree 2 is called a square root and a root of degree 3, a cube root. Roots of higher degree are referred by using ordinal numbers, as in 4th root, 20th root, etc. For example, 2 is a square root of 4, since 22 equals 4. A 2 is also a square root of 4, since 2 equals 4. A real number or complex number has n roots of degree n. While the roots of 0 are not distinct, the nth roots of any other real or complex number are all distinct. If n is even and x is real and positive, one of its nth roots is positive, one is negative, and the rest are complex but not real. If n is even and x is real and negative, none of the nth roots is real. If n is odd and x is real, one nth root is real and has the same sign as the radicand, while the other roots are not real. Roots are usually written using the radical symbol or radix or, with or denoting the square root, denoting the cube root, denoting the 4th root, and so on. In the expression, n is called the index, is the radical sign or radix, and x is called the radicand. When a number is presented under the radical symbol, it must return only one result like a function, so a non-negative real root, called the principal nth root, is preferred rather than others. An unresolved root, especially one using the radical symbol, is often referred to as a surd or a radical. Any expression containing a radical, whether it is a square root, a cube root, or a higher root, is called a radical expression, and if it contains no transcendental functions or transcendental numbers it is called an algebraic expression. In calculus, roots are treated as special cases of exponentiation, where the exponent is a fraction. Roots are particularly important in the theory of infinite series. The root test determines the radius of convergence of a power series. Nth roots can also be defined for complex numbers, and the complex roots play an important role in higher mathematics. Galois theory can be used to determine which algebraic numbers can be expressed using roots, and to prove the Abel-Ruffner theorem, which states that a general polynomial equation of degree 5 or higher cannot be solved using roots alone. This result is also known as the insolubility of the quintic. History: the origin of the root symbol is largely speculative. Some sources imply that the symbol was first used by Arabic mathematicians. One of those mathematicians was Abu al-Hasan ibn Ala al-Qazadar. Legend has it that it was taken from the Arabic letter O euro, which is the first letter in the Arabic word O degree O plus or minus a euro. However, many scholars, including Leonhard Euler, believe it originates from the letter R, the first letter of the Latin word radix, referring to the same mathematical operation. The symbol was first seen in print without the vinculum in the year 1525 in Dikos by Christoph Rudolph, a German mathematician. The term surd traces back to Al-Khwa Rizmar, who referred to rational and irrational numbers as audible and inaudible, respectively. This later led to the Arabic word ox micron euro for a rational number being translated into Latin as surdless. Gerard of Cremona, Fibonacci, and then Robert Ricord all used the term to refer to unresolved irrational roots. In the U.S., an early contributor to its understanding was a little-known African-American mathematician, Charles T. Giordani, who in 1843 proposed an innovative solution, a consensus method of extracting the 4th root. Example. Definition and notation. The nth root of a number x, where n is a positive integer, is a number whose nth power is x. Every positive real number x has a single positive nth root, which is written. For n equal to 2 this is called the square root and the n is omitted. The nth root can also be represented using exponentiation as x1/n. For even values of n, positive numbers also have a negative nth root, while negative numbers do not have a real nth root. For odd values of n, every negative number x has a real negative nth root. For example, a 2 has a real 5th root, but a 2 does not have any real 6th roots. Every non-zero number x, real or complex, has n different complex number nth roots including any positive or negative roots. See complex roots below. The nth root of 0 is 0. The nth roots of almost all numbers are irrational. For example, all nth roots of integers, or in fact of any algebraic number, are algebraic. For the extension of powers and roots to indices that are not positive integers, see exponentiation. The character codes for the radical symbols are square roots. A square root of a number x is a number which, when squared, becomes x. Every positive real number has two square roots, one positive and one negative. For example, the two square roots of 25 are 5 and a 5. The positive square root is also known as the principal square root, and is denoted with a radical sign. Since the square of every real number is a positive real number, negative numbers do not have real square roots. However, every negative number has two imaginary square roots. For example, the square roots of a 25 are 5i and a 5i, where I represents a square root of a 1. Cube roots. A cube root of a number x is a number whose cube is x. Every real number x has exactly one real cube root, written. For example, every real number has two additional complex cube roots. Identities and properties. Every positive real number has a positive nth root and the rules for operations with such surds are straightforward. Using the exponent form as in normally makes it easier to cancel out powers and roots. Problems can occur when taking the nth roots of negative or complex numbers. For instance, whereas, when taking the principal value of the roots. See failure of power and logarithm identities in the exponentiation article for more details. Simplified form of a radical expression. A radical expression is said to be in simplified form if there is no factor of the radicand that can be written as a power greater than or equal to the index. There are no fractions under the radical sign. There are no radicals in the denominator. For example, to write the radical expression in simplified form, we can proceed as follows. First, look for a perfect square under the square root sign and remove it. Next, there is a fraction under the radical sign, which we change as follows. Finally, we remove the radical from the denominator as follows. When there is a denominator involving surds, it may be possible to find a factor to multiply both numerator and denominator by to simplify the expression. For instance, using the factorization of the sum of two cubes. Simplifying radical expressions involving nested radicals can be quite difficult. It is not immediately obvious, for instance, at infinite series, the radical or root may be represented by the infinite series. With this expression can be derived from the binomial series. Computing principal roots, the nth root of an integer is not always an integer, and if it is not an integer then it is not a rational number. For instance, the fifth root of 34 is where the dots signify that the decimal expression does not end after any finite number of digits. Since in this example the digits after the decimal never enter a repeating pattern, the number is irrational. The nth root of a number a can be computed by the Nth Root Algorithm, a special case of Newton's method. Start with an initial guess xo and then iterate using the recurrence relation until the desired precision is reached. Depending on the application, it may be enough to use only the first Newton approximant. For example, to find the fifth root of 34, note that 25 equals 32 and thus take x equals 2, n equals 5 and y equals 2 in the above formula. This yields. The error in the approximation is only about 0.03%. Newton's method can be modified to produce a generalized continued fraction for the nth root which can be modified in various ways as described in that article. For example, in the case of the fifth root of 34 above, digit-by-digit calculation of principal roots of decimal numbers. Building on the digit-by-digit calculation of a square root, it can be seen that the formula used there, or, follows a pattern involving Pascal's triangle. For the nth root of a number is defined as the value of element and row of Pascal's triangle such that, we can rewrite the expression as. For convenience, call the result of this expression. Using this more general expression, any positive principal root can be computed, digit by digit, as follows. Write the original number in decimal form. The numbers are written similar to the long division algorithm, and, as in long division, the root will be written on the line above. Now separate the digits into groups of digits equating to the root being taken, starting from the decimal point and going both left and right. The decimal point of the root will be above the decimal point of the square. One digit of the root will appear above each group of digits of the original number. Beginning with the leftmost group of digits, do the following procedure for each group, starting on the left. Bring down the most significant group of digits not yet used and write them to the right of the remainder from the previous step. In other words, multiply the remainder by and add the digits from the next group. This will be the current value C. Find P and X, as follows. Let P the part of the root found so far, ignoring any decimal point, determine the greatest digit such that. Place the digit as the next digit of the root, that is, above the group of digits you just brought down. Thus the next P will be the old P times 10 plus X. Subtract from to form a new remainder. If the remainder is 0 and there are no more digits to bring down, then the algorithm has terminated. Otherwise go back to step 1 for another iteration. Examples: find the square root of 152.2756. 1 2 3 4 / // 0152.2756. 01 100 100 12 plus 101 201 11 per mil 1 currency 100 100 22 plus 101 201 21 x equals 1, 01 y equals 100 100 12 plus 101 201 12 equals 1 plus 0 equals 1, 52 100 1 10 22 plus 101 2. 11 21 per mil 52 currency 100 1 10 32 plus 101 2 11 31 x equals 2, 44 y equals 100 1 10 22 plus 101 2 11 21 equals 4 plus 40 equals 44. 08 27 100 1 120 32 plus 101 2 121 31 per mil. 827 currency 100 1 120 42 plus 101 2 121 41 x equals 3, 0729 y equals 100 1 120 32 plus 101 2 121 31 equals 9 plus 720 equals 729, 9856 100 1 12 30 42 plus 101 2 12 31 a. 41 per mil 9856 currency 100 1 12 30 52 plus 101 2 12 31 51 x equals 4, 9856 y equals 100 1 12 30 42 plus 101 2 12 31 41 equals 16 plus 9840 equals 9856, 0000 algorithm terminates, answer is 12.34. Find the cube root of 4192 to the nearest hundredth. 16 124 3 / / 004 192.000000000. 004 100 100 13 plus 101 301 12 plus 102 302 11 per mil 4 currency 100 100 23 plus 101 301 22 plus 102 302 21 x equals 1, 001 y equals 100 100 13 plus 101 301 12. Plus 102 302 11 equals 1 plus 0 equals 1, 003 192 101 10 63 plus 101 311 is 62 plus 102 312 is 61 per mil 3192 currency 101 10 is 73 plus 101 311 is 72 plus 102 312 is 71 x equals 6. 003096 y equals 101 10 is 63 plus 101 311 is 62 plus 102 312 is 61 equals 216 plus 1080 plus 1800 equals 3096, 09600 100 a 1 a 160 a 13 plus 101 a 3 a 161 a 12 plus 102 a 3 a 162 11 a. Per mil 96,000 currency 100 a 1 a 160 a 23 plus 101 a 3 a 161 a 22 plus 102 a 3 a 162 a 21 x equals 1, 077 281 y equals 100 a 1 a 160 a 13 plus 101 a 3 a 161 a 12 plus 102 a 3 a 162 11 equals 1 plus 480 plus 76,800 equals 77,281, 018,719 000 100 a 1 a 1610 a 23 plus 101 a 3 a 1611 a 22 plus 102 a 3 a 1612 a 21 a per mil 18,719,000 currency 100 a 1 a 1610 a 33 plus 101 a 3 a 1611 a 32 plus 102 a 3 a 1612 a 31x equals 2, 015 571 928 y equals 100 a 1 a 1610 a 23 plus 101 a 3 a 1611 a 22 plus 102 a 3 a 1612 a 21 equals 8 plus 19,320 plus 15,552,600 equals 15,571,928, 003 147 07 to 000 100 a 1a. 16,120 a 43 plus 101 a 3 a 16,121 a 42 plus 102 a 3 a 16,122 a 41 a per mil 3,147,072,000 currency 100 a 1 a 16,120 a 53 plus 101 a 3 a 16,121 a 52 plus 102 a 3 a 16,122 a 51 x equals 4. The desired precision is achieved, the cube root of 4192 is about 16.12. Complex roots. Every complex number other than 0 has n different nth roots. Square roots. The two square roots of a complex number are always negatives of each other. For example, the square roots of a 4 are 2i and a 2i, and the square roots of I are. If we express a complex number in polar form, then the square root can be obtained by taking the square root of the radius and halving the angle. A principal root of a complex number may be chosen in various ways, for example, which introduces a branch cut in the complex plane along the positive real axis with the condition 0 per mil IAA 2i euro, or along the negative real axis with AI euro IAA per mil I euro. Using the first, last, branch cut, the principal square root maps to the half plane with non-negative imaginary, real, part. The last branch cut is presupposed in mathematical software like MATLAB or Scilab. Roots of unity. The number 1 has n different nth roots in the complex plane, namely, where these roots are evenly spaced around the unit circle in the complex plane, at angles which are multiples of. For example, the square roots of unity are 1 and a 1, and the fourth roots of unity are 1, a 1, and nth roots. Every complex number has n different nth roots in the complex plane. These are, where I is a single nth root, and 1, ai per mil 2, ai per mil now 1 are the nth roots of unity. For example, the four different fourth roots of 2 are. In polar form, a single nth root may be found by the formula. Here R is the magnitude of the number whose root is to be taken. If the number can be written as a plus b, then also is the angle formed as one pivots on the origin counterclockwise from the positive horizontal axis to array going from the origin to the number. It has the properties that and, thus finding nth roots in the complex plane can be segmented into two steps. First, the magnitude of all the nth roots is the nth root of the magnitude of the original number. Second, the angle between the positive horizontal axis and array from the origin to one of the nth roots is, where is the angle defined in the same way for the number whose root is being taken. Furthermore, all n of the nth roots are at equally spaced angles from each other. As with square roots, The formula above does not define a continuous function over the entire complex plane, but instead has a branch cut at points where ia/an is discontinuous. Solving polynomials, it was once conjectured that all polynomial equations could be solved algebraically. However, while this is true for third-degree polynomials and fourth-degree polynomials, the Abel-Ruffney theorem shows that this is not true in general when the degree is 5 or greater. For example, the solutions of the equation cannot be expressed in terms of radicals. For solving any equation of the nth degree numerically, to obtain a result that is arbitrarily close to being exact, see root-finding algorithm. See also, Nth root algorithm, shifting Nth root algorithm, irrational number, algebraic number, nested radical, 12th root of 2, superroot, references. External links.